Welcome to When Partitioning Indexes Hurts Performance and How to Fix It on the final day of the SQL Pass Summit this year. Thank you all for showing up. I know that there's a lot of parties and things going on. This slide sends you two different messages. It tells you to silence your cell phone, but then if you look at the picture in the background, it also tells you to turn to one another and talk throughout the session. You can choose which of these messages you would like to follow. It is up to you. I have conveyed the message to you. There are a lot more messages on this slide, and on this slide, I actually want you to pursue all of the messages. One of my very favorite things about Pass is that Pass has a lot of ways to let people be involved throughout the year, and Pass also brings new speakers into the community, brings new speakers up to this podium. I encourage you to share your knowledge and consider presenting to your local user group, submitting a session to a SQL Saturday, trying out the speaker idol competition to get a spot at Summit, submitting sessions to Summit. Pass has helped me become a speaker and grow as a speaker, and it is here to help you. Maybe you've been coming to summits for a while and you never considered being a speaker. It's not too late to consider that. So think about sharing your knowledge and becoming a different part of the community as well. Lots of ways to do that. Please tip your speakers throughout the summit by submitting session evaluations. That is the way that you can tell us, what did you like? You can tell the organizers of the conference, what do you want to see in the future? And I'm ashamed I didn't even realize this. Did you attend the keynotes? Did you like one of the keynotes better than the other? You can submit feedback for the keynotes as well and tell the conference organizers what you want to see. And we listen to your feedback as speakers. The Pass organizers listen to it too. It will help a lot. My name is Kendra Little. I make online SQL Server training at a site called SQLworkbooks.com. And bio slides I really like when I have to confront a bio slide and fill it out, because you have to think about, okay, how do I identify? Like, who am I? And when I was looking at this slide, I've had a lot of different kind of roles. I've been a DBA. I've helped found a consulting company and build the consulting process. I've written a lot of training, and I thought, okay, who am I? And this quote from Adam Savage came to mind, and the real quote's on this screen, but in a sense he says, what makes humans different is that we like to use tools and we like to tell stories, and we can do that. And when we make something, we are combining both telling stories and using tools. That really resonated with me, that combination of using tools and narrating a story is what I really love. And today, the tools that we're working with and the story that we're going to tell is about table partitioning in SQL Server, which is a feature that I've loved for a long time and been interested in for a long time, but now it's even more relevant than ever and more accessible than ever, because Microsoft made a huge change in Service Pack 1 of SQL Server 2016 and changed what edition many things are available in, including table partitioning. If you're using SQL Server 2016, Service Pack 1 or higher, you can now use table partitioning in Standard Edition, which is really exciting and gives us a lot more options and maybe a really good reason to upgrade if we're on a lower version of SQL Server in some cases. But table partitioning is often very misunderstood in SQL Server, and I misunderstood this myself for a long time. The marketing materials, when table partitioning first came out, the marketing materials were all like, this is fully transparent. You don't need to change your application at all. You partition the table and everything just works. And that's kind of true. You can partition the table and the queries you wrote before can still use the table, but the second part of this is not true. I just assumed if I'm breaking my table into chunks, my queries are going to get faster. Is something slow? Just sprinkle some partitioning on it. It'll speed up. And that is not necessarily true. Table partitioning is a fantastic feature for helping me load large chunks of data very quickly without lots of locks that bother my users. It can let me remove large chunks of data. It can help me distribute chunks of data across different file groups that maybe are on different disks. And if I'm very clever about how I write my queries, I can get great performance. But what you will see in this session is that there are some query patterns where if we take our table, we take a B-tree index, and we change it into a bunch of smaller B-tree indexes, the performance may get slower for that query because things have to work differently. So we'll walk through 3 different patterns where we may get performance regressions after we partition a table. We'll talk through different options on how to speed it up and what the trade-offs are for those options. These will be both T-SQL options as well as indexing options. Sadly, I don't have time to dig into everything I'd like to talk about because we've just got 75 minutes. We will be touching on column store indexes and partitioning. We'll be talking both about row store indexes and about new column store indexes. My demos have some non-clustered column store in them. I don't get to dig into the depth of all of those features. If you could stay late by a couple days, maybe we'll get there. The demo data we'll be looking at today is based on a free data set from the United States government. They publish a list of the most popular baby names. We have a little bit of lag in how this is published. It comes out on Mother's Day each year. You can get it from data.gov. What I've done is I've taken that data, which is aggregate data, I've put it into a SQL Server database, and I've used it to create some fake row-level data, right? So what I get is for each year, we had 5,000 babies named Henry. So you'll be seeing some tables where I've created 5,000 rows, one for each Henry, because when we're talking about table partitioning, when we partition a table, we usually have a lot of rows to partition. We'll be comparing the performance between 2 different tables. One of them is partitioned. Technically speaking, every table in SQL Server has at least one partition. So one of these tables, dbo.firstname by birth date, it has a single partition. The table pt.firstname by birth date, so same name, different schema, has been partitioned into year chunks. Both of the, for this demo, I didn't want things like create index to take 7 minutes on my laptop, so I have here the data from babies named in 1970 and later is what we're looking at today. There's about 146 million rows in each table, and our partitioning column on the partition table, our partitioning key, is a column named fake birth date stamp. I mentioned that I'm faking out those individual rows, so it's nobody's actual birth date. It is a fake birth date stamp. The partitions are somewhat evenly sized, but because of population growth, I do have more rows in the partitions that are recent years rather than in the older ones, but the partitions are not huge. They're about 60 megs to 80 megabytes per partition, right? So tried to keep the data small so that if you want to download the scripts from the past site and replay things, it's not all huge. Here is our partition function for our partition table. The column is a datetime2 with precision 0, and I use some dynamic SQL to just generate a script. The important thing is it is partitioned into year chunks using that column. I have created some row store indexes both on the non-partitioned table and the partitioned table. You'll be seeing these in the demos. One of the indexes is on birth year. They both have an index on birth year, a row store index. Birth year is a computed column. They also both have a non-clustered index on first name ID, so they match. I haven't cheated and made them different. We are testing out column store on the new table. We're using a non-clustered column store just so I can show you, okay, how does the row store do? How does the column store do? And these are the columns that I have in the column store index. We do not have one column in the column store index. It's called birth year. It's that computed column. We cannot put computed columns in non-clustered column store indexes. In SQL Server 2017, you now have the option to put non-persisted computed columns in clustered column store indexes only, but you'll see that there is an interesting way that birth year is going to, even though birth year isn't in our non-clustered column store index, it's actually going to sneak into our execution plans in an interesting way. So relatively speaking, in terms of tables in the actual world, this is a pretty small table. Big enough to do some demos, but notice that the times that you see on the screen when we're running through things, like these times, like on larger tables, the latencies would be magnified, because this really is a pretty small table, but still we're going to see some queries who are notably faster before we partition the table. They get slower when we partition it, and we'll talk about why. Our first problem query is called the aggregator. And the aggregator is looking at the tables. You know, we're going to run it once against non-partitioned, once against partitioned. And it's looking at babies who were born between 2001 and 2015. It's grouping by the year they were born and just counting the number of babies born in that year. So let's go ahead and test this out and see how this does with partitioned and non-partitioned tables. So now we get to the fun stuff. We get to the demos. All right, I've got, yep, I think there, yes, yes. It's always successful when we get to the demo. So I've run a setup script against the data set. This is available. All the scripts are on the PASS site, and at the very top of the script, it tells you where to download a starter 41 meg zipped backup of the data names. I didn't want to make you download a whole huge backup file, so you've got a small file and then the script expands it out. So I've already run that. Here is the aggregator query. I'm going to run this first against the non-partitioned table. And when I run it against the non-partitioned table, I already have my execution plans on, and I'm going to look at those. And I run this against the row store non-partitioned table, and it doesn't take super long. How long did it take? I'm going to look in my execution plan and open the properties pane. And since I'm running 2017 here, but since SQL Server 2014 Service Pack 2, I believe, we now have the ability in our execution plans to see query time stats in these actual plans. I have the select operator highlighted, and I can see that my elapsed time was 1.9 seconds. My CPU time for the whole query was 6.5 seconds. So, you know, this is my baseline. I haven't partitioned the table. Looking at my plan, I can see that I am doing an index seek on the table because my query says I only want birth year between 2001 and 2015, and my index seek is on my non-clustered index on birth year. I can index computed columns in SQL Server, so I've indexed this one, and it's able to go straight to the birth year. It does have to read a bunch of rows for these years, right? I'm looking at a big range, but then it uses those rows, counts them, gathers its parallel threads, and then brings the data back to me, and it does it pretty quickly, right? We're under 2 seconds. Well, I've got this same index on birth year on my partition table, and I have that non-clustered column store index on the partitioned table. So if I run this against my partition table, I mean, I have a lot. I've partitioned it, and I have a column store. This is surely going to be faster, right? This is surely going to be faster. Well, I've still got my execution plans on, and I start up my query, and wait, it's been more than 2 seconds. We're at 7 seconds, it's still go. I partition my table and, well, why could this be slower? Whenever I change anything in SQL Server. Even sometimes if I just change my data, there is an opportunity for things to get slower. And this took, let's see how long this one took, looking at the properties of my execution plan, going into my query time stats. Well, okay, this is a little different. We got 17 seconds of CPU time, and then our elapsed time was 17.5 seconds before it was under 2 seconds. So yeah, a little bit of a regression. Well, what's up? One thing to notice is, okay, our CPU time and our elapsed time are now roughly equal. Before, I had more CPU time than elapsed time. Before, it was using multiple cores to execute this query. And now, when they're about the same, I'm getting single-threaded. My cost threshold for parallelism setting on my instance is set to 100. The default is 5. The default is really low. So I've upped it to 100. And when I ran that first query against the non-partition table, it estimated a cost that was high enough. It was above 100. It qualified to go parallel. And now we've got super zoom there. Wow, that was like extra zoom. But here, my estimated subtree cost is only 59. It didn't qualify to go parallel, so it had to do everything with a single thread. Well, all right, what happened? It did decide to use the column store index scan. Okay, well, how long did that take? One of the cool things about these CPU time properties is that we can look at it per operator. It's a little tricky in terms of how it's displayed. For our column store index scan, we are in batch mode. Column store indexes enjoy the opportunity to get super fast batch mode, where the iterator can suck in and process more than one row at a time. We don't have to be all 1Z, 2Z, 3Z, 4Z. We can deal with batches. And that's good for something like count a bunch of rows. Well, okay, that seems promising, though. How long did this take? I'm going to look at how long did this operator take. When an operator is in batch mode, in an actual plan, these values are reported just for the operator, not for any children. And this one doesn't, we're at the right, we don't have any children anyway. So just doing the column store part took about 1.7 seconds. Okay, well that's just a small fraction of our execution time, so let's keep looking. I'm gonna go to the left. There's a compute scalar here. Okay, well what are we computing? I'm gonna hover over it and go down. We are computing the birth year column. The non-clustered column store index has the fake birth date stamp column in it. It can't have the birth year computed column in it. You know, it's not allowed in a non-clustered column store. And even if we were in clustered, it's not allowed to be persisted. It's not allowed to be recorded on disk. It would have to compute it there too. So what SQL Server has figured out is, oh, your birth year column is just the year function on top of this other column. I can look at every single fake birth date stamp, run the year function against it, and figure out what birth year is, and then feed all of them into a filter so that I can, so I'm looking at pulling every row out of my column store, doing a compute scalar on it, and then doing a filter. Well, how long does this compute scalar take? I did get batch mode for it. That's good. But when I look at my actual time statistics, whoa, and this is just for this operator, we spent a long, long time figuring out the birth year for every single row. So our SQL Server was so excited. I mean, bless its heart. It was like, I've got this column store index. It's going to be amazing. I'll just figure out birth year for every row. And then I'll figure out which ones are in the range you want. But it thought it was going to be cheap. It thought it was going to be cheap enough that it only gave us one thread. And then I think this is undercosted. It wasn't really cheap at all. So okay, well, so this whole thing with we're testing out this column store on our dev instance. Okay, recomputing the birth year, that's not partitioning's fault. So let's just say, okay, SQL Server, against our partition table, I'm running against the partition table. I just don't use the non-clustered column store index. You have the same index on birth year. You have the same non-clustered row store index on birth year that we have on the non-partition table. So just use that. In the version of SQL Server I'm running, when I use this hint, ignore non-clustered column store index, I'm also not going to get batch mode anymore. So I'm going to be back in row mode. I'm going to lose that cool batch mode that's available because a column store index is on the table. But my non-partition table was in row mode too, so you know that's fine. We should be about the same, right? So I'm going to go ahead and run this query. And I'm also doing statistics, I/O, and time, so I get another measure. And this takes not 2 seconds. Well, let's run it again. Maybe the data just wasn't in memory. I want to be fair. I don't want to cheat it. OK, it was a little faster on the second run now that I had things warm in my cache. But when I look at my query time stats, hey, my elapsed time is 3.6 seconds. That the non-clustered row store index has birth year in it, so it doesn't have to recompute birth year for every row. We didn't have to do all that 13-second mess. But when the table wasn't partitioned, this was like 1.9 seconds, right? We were under 2 seconds. Our CPU time is also higher. Our CPU time is 13.6 seconds. So we are a bit slower than the row store table was. And if we run this repeatedly, we'll see similar things. Now, we were costed out at a level where we did get back to the parallel plan, right? Like we got against the non-partitioned table, we got parallelism, but it was slower just because the table was partitioned. If we run these repeatedly, we will see similar run times. The non-partitioned row store index on birth year. So before we partitioned our table, elapsed time under 2 seconds. After we partitioned the table using the same definition of the index, we're around 3 seconds, and our CPU time is higher as well. If we let it recompute birth year with a column store for every row, it gets much, much slower. Why is this? Let's take a quick look at some slides to just diagram out a little bit about what's going on, and then we'll talk about speeding it up. Before we partitioned this table, the index on birth year, and this, it had a lot more pages than this. This is simple. I couldn't draw every single page. I tried. But before we partitioned our index, we had a lovely balanced tree of 8K pages. The earlier birth years are on one end, the higher birth years are on the other. So when we're running our query and we're just going to find all the rows where the birth years between 2001 and 2015, it's able to seek straight to those rows, and it's able to use multiple threads to do it if we cost out, if we're estimated to be expensive enough to get parallelism according to our settings. This was under 2 seconds. We need to count the rows between this range, right? So we not only want to find the rows, we also want to count them. Well, they're in order, right? We're grouping by year, and they're in order by birth year. So SQL Server knows that, hey, I can stream this right into my counting because the data is already ordered in the index by birth year. So I know that the thread reading it over here has low birth years, and I can stream this data and count it as it comes back to me. It is already ordered by what I'm grouping by. So in the plan, what we see is a stream aggregate operator. I have added the dinosaurs. I think they explain better about what's going on. But you just see in SQL Server, you just see stream aggregate operator without the dinosaurs. Things change once we partition this index. We no longer have a single structure in our partitioned index. The index is aligned. This non-clustered index is aligned with our table, and our table is partitioned by year. So our non-clustered index is now a lot of little B-tree indexes together, each for a different year. This is kind of a weird situation because birth year is a computed column, right? Birth year is actually based on the partitioning key, which is fake birth date stamp. Birth year is year, fake birth date stamp. But SQL Server doesn't actually understand that those are related. It knows the partitioning key is fake birth date stamp. It knows the key of our index is birth year. They are different keys in this case. So it knows that within each partition, it's ordered by birth year, and it knows that the index is partitioned by these ranges we've specified of fake birth date stamp, but the partitioning definition is flexible. When we create our partition function, we could decide to have one partition that has multiple years in it. We don't have to make them even. We could make one a month, right? We just define the boundary points. So it really doesn't deeply understand an association between these, and it doesn't understand that it doesn't have to look at every single partition. It says, oh, well, I should check every single partition to see if you've got data in the years I want. It doesn't understand it could just eliminate some. We check them all. This means it cannot stream the counting. It thinks, oh, I might find, in that partition for the year 1880, I might find some data for the year 2007. It doesn't know. And so it cannot stream into that aggregate operator. It has to collect and count as it goes in a lovely place called tempdb. And it puts the data into buckets and says, okay, I've got to get all the data into these buckets, count it all up before I can release any of that information to the rest of the plan. It's not already perfectly ordered for me. So in the plan, we get a hash match operator. We are bucketing, and then we are counting before we move on. And this operator acts differently. Hash match, I'm not saying this is a bad operator, but one of the things about hash match aggregate versus stream aggregate is that hash match is a blocking operator. I've got to count all the data, make sure I'm finished, and then the plan can go on. With stream aggregate, because it knows the data is ordered, once it finishes with a part of the index, it knows, hey, I finished counting for this segment. I can pass that information on, and other parts of the plan can keep going. They don't have to wait on me because I can stream information out. So by partitioning, we've gotten to a blocking operator in this index. So let's go ahead and tune it. Go back to demo. All right, let's look at some fixes. And before I go to the fixes real fast, I do want to show you one thing about the plan. How can I prove that it didn't eliminate partitions? Let's go back to my execution plan. This is the execution plan for the query where the partition table, not using the column store. And if I go, I see index seek, right? That seems good. I'm seeing an index seek. And I look at my properties on my index seek. So I have my index seek highlighted, and how do I tell how many partitions it looked at? In an actual execution plan, I can see two things, and they're a little confusing, the wording. There's actual partition count, and then there's actual partitions accessed. I accessed the 63 partitions in my table. The partition numbers was from partition 1 to partition 63. So I wasn't able to eliminate. I looked into all of those partitions. All right, well, how can we speed this up? Well, one thing we can create, and I'm going to get this going because it does take a couple seconds to run. On a partitioned table, we have the option to create a non-partitioned index. When I run create index, and let me just zoom in on the command while it's running. When I run create index, if I don't specify anything in the on, if I don't tell it what to create the index on, it assumes, oh, this is a partition table. I'm going to go ahead and create this on the partition scheme that the table's on. I'm going to align it with your existing partition scheme, so it's also partitioned. In this case, I've said on file group, and this is my file group name, do not create this index on the partition scheme. Instead, go create it on this file group. This will be created just like in my other table. Like I've said, don't partition this index. So now I have a partitioned clustered index for this table, and then a non-clustered row store index on birth year that is just a single tree. It is not broken into those year-long chunks at all. This index isn't super cheap. All of the rows in my table are going into it. It's going to take about 2 minutes to create. Now, you might wonder, like, what? So this sounds great. I can have my exact same non-clustered index I used to have. Well, it is great, and I'm naming this non-aligned. This is what's called the non-aligned index. It is great that we can do it, but it has some big downsides. Our table's broken into year-long chunks. That means I can do things like, when new data comes in, create a staging table that's empty, put a year's worth of data in it outside of the table, do some magic with my partition function and partition scheme to make sure the year's in there. And then the only thing my customers see is I momentarily just switch that data in and do a metadata switch to say, oh, this data from the staging table is now in my table. Like, wham, requires a schema modification lock, but because it's a metadata change only, it's instant. So I can move a whole year's worth of data into the table fast. But what happens if I have a non-aligned index on the table, right? I'm trying to switch a new year into the table, but where would it go in that index that isn't broken into chunks? It would have to like actually do a huge insert. I cannot switch data in or switch data out if I have non-aligned indexes on the table. All of the indexes have to be aligned along the same boundary points. So I've created this index, and that's great. If I look at my query, I may see something new. Now, I'm going to just do estimated plan for this. This is against the partitioned table, but I don't have the hint saying don't use the column store. So the question is, will it use my new non-aligned index, or will it want to use the column store? Well, it's really, really excited about that column store index, even though it doesn't have birth year in it. It doesn't know it's going to take 19 seconds. It's just, I can't blame it. I love column store indexes too, but in this case, it's not a good choice. So we do still have to tell it, no, really, like that column store index isn't good for this query. If I say ignore non-clustered column store index, what I've essentially done is give it an index to use that's just like in our first plan, right? We got a index seek on the non-aligned index, and if I go over and look at the properties of my select, find my query time stats, sure enough, I mean, we're a little bit over 2 seconds if I run enough. It basically ends up being the same performance, depending on how many projectors I have plugged in and a variety of things going on my laptop, because I've given it the same structure it had before the table was partitioned. But now that I've done this, I cannot switch partitions in and out. And there's a cool feature that we got. I think we got this one in 2016. We got the ability to say, oh, I want to truncate individual partitions. Take partitions 1 to 4 and truncate them. If I try to do this, I now get the error, index non-aligned is not partitioned, but the table uses a partition function, pf fnbd. The index in table must use an equivalent partition function. The wording is a little weird here because technically you could have 2 partition functions that have the same definitions and it would be fine with that. It just wants them to have the exact identical chunks the data is broken into. So there's a big downside to creating these non-aligned indexes to get the same performance we had before partitioning the table. We lose this huge benefit that we get with table partitioning to manage data at the partition level. It's kind of a big bummer. We could potentially disable the non-clustered index, do our partition loading and switching, and then rebuild it at the end, but the bigger our table, the longer and longer and longer that's, I mean, right? This is not awesome. So what else can we do? What other fixes might be better? Maybe we can rewrite our query to get partition elimination, right? There's 2 reasons our row store query got slower, and then even our query with the column store index, right? It didn't understand with birth year that it could eliminate partition. So I'm going to change my query a little bit. Instead of using birth year in my predicate, I'm going to say, okay, let's go look at the partitioning key column, and I want fake birth date stamp greater than or equal to or less than. I'm using a different column instead of the computed column, and this column is the partitioning column. Can we get better performance? Let's get this going. how many partitions will be used in the plan. I am still using birth year to group by and in the select. I haven't gotten it out of the query entirely. I have simply changed the predicate. And by doing this, and I don't have a hint in here, notice I have no hints, it said, oh, I am going to use the column store index still. But there's a difference here. Before, it didn't understand birth year. Before, remember, we had a big old filter operator in here. It did everything through the compute scaler and then put it into a filter. Now we don't have a filter. Now we have a column store index scan. And when I look at the properties of the column store index scan, I'm going to get the query back on the screen here. Because I'm using in my predicate, because I'm using the partitioning key, SQL Server is able to say, oh, that data, the predicate's on the partitioning key, that data is in partition numbers 44 to 58. So I only need to pull that data out of my column store index. And yeah, I do still have to recompute birth year for it, but it's not all the rows in the table. Thank goodness. I'm still single-threaded, but I'm doing this compute scalar on just a lot fewer rows. So it's going to be faster. And when I look at my select and I look at my query time stats, this isn't 19 seconds. It's 6 seconds. So if on our partition table, we help it understand what partitions we want data out of, and we make sure that it's eliminating partitions, it just has less work to do, even though I'm still using that birth year computed column. So this is good, but we still are not at 2 seconds or faster, which is kind of a big bummer. Well, is there something else that we can do for this poor query? Well, here's a little summary of where we're at, because I've shown you a lot of queries. The time we're attempting to match, hopefully without a non-aligned index, the original query was under 2 seconds, bless you. Now that we have a rewritten query and a partitioned column store index, and we're getting partition elimination, we're getting closer. But what can we do? I think it is still kind of under-costing this. We still aren't going parallel. And our original query against the row store index, it was getting a higher estimated cost, and it was going parallel. I could change my cost threshold for parallelism on the instance, but that's for everything. And maybe this is a good level for my workload. Is there a way I can make this individual query get to use multiple cores? Well, yes, there is a couple of ways. Has anyone actually used trace flags or hints to force parallelism? You can admit it, it's a safe space. So technically what they've done is undocumented. I have to share that with you. But there are hints that it may soon become documented because of what you're going to see. There is a trace flag, 8649, that has been around for a little while that you can, in an undocumented way, experiment with. Fully undocumented, I'm not saying it's documented at all. I think I've said that 8 times now, right? So fully disclaimered. But on SQL Server 2016, Service Pack 1, Cumulative Update 2, we got not an announced feature, but a very clever person named Dimitri posted on his blog, queryprocessor.com, hey, there is a hint. It's not in Books Online, and it's not in, we have these new hints we can use that are in sys.dmexec valid use hints. This hint is not in that list, but he found, using deep scientific ways that I don't even begin to comprehend, that this hint exists. And the hint, I mean, look at the name of it. I'm going to enable a parallel plan preference. I'm going to say, please give me a parallel plan. Well, let's try this out. It hasn't been announced or documented, but look, I can put it in this nice syntax, use hint, enable parallel plan preference. Yes, please. So here we go. I'm saying, give me more cores, and that wasn't 6 seconds. It liked my preference. It liked my preference. We've got double arrows. So looking at my column store index scan, I've got my partition elimination still because I am now using my partitioning key in the predicate. I've got parallelism. I've got batch mode because I'm using my column store index. I get all the magic. And let's go over and look at what our official time is. Our official execution time in query time stats. We are just barely over 2 seconds. If I ran it again, maybe I'd get just below, right? Now, we do still have a hash match operator. The data in the column store index is being consumed in batch mode, and we don't have this guaranteed sort so that we can stream the data into counts. So we don't have that faster non-blocking stream aggregate operator, but batch mode is really good. It makes up for the fact that we don't have a stream aggregate, and we've got batch mode sort of supercharging our hash match aggregate. Yeah. There was talk, I believe, in a session from the Microsoft team that they are working on allowing us, without using trickery and undocumented things, they are going to work on ways to have batch mode against row store indexes in the future, because batch mode's awesome. So, woohoo! So there's a couple different ways we can speed up this query, and we can, we got this regression against the table. I really like fix 2 with the rewrite, right? But I did have to rewrite my query, and then I did kind of have to use a hint to get the column store to be that fast. When we have a regression like this, my preference is to rewrite the query. If we have to create a non-aligned index to get the performance that we had before, I do think it's a huge bummer, because even if we aren't using partition switching or partition truncate now, we lose the ability to do things like rebuild individual partitions on that non-clustered index. I've got an ever-growing single index that I have to maintain, right? I really like keeping aligned indexes, because it's healthier for the table, and it lets you use more of the features from partitioning. But if we have to, we can. Yes, question? Okay, so the comment is something that we are going to see something similar to in the next demo. So it is a great comment. The comment has to do with the fact that we have ways to know which partition every row in the table is in, and there are ways we can leverage that, and we are actually going to see that in problem number 2. So fantastic comment. I won't go too deep there because we're going to get there. Would we have the same problem if we did partitioning on the computed column? If we use the computed column as our partitioning key, and you are able to do that, we would be able to eliminate on the computed column, but beware, we would run into a lot of other problems, because computed columns are a little bit pathological in SQL Server. We might have, I'm not getting parallelism and I don't know why. We might have all sorts of different weird issues. There is an excellent article by a fellow called Paul White on a lot of the things that can go wrong with computed columns if you use them in different ways in SQL Server. It's a long read. I highly recommend it. I'll do a blog post for the session and follow up and put the URL in there. But yeah, we technically could do the computed column as the partitioning key. Because of a lot of the weirdness we would run into, I don't generally recommend doing computed columns as partitioning key. Yeah, I wish we didn't have those issues. Yeah.
What about just normalize and create this code, like physical code, and do like calculate the source here?
What if we did, is your question, what if we didn't use the computed column and actually just said, okay, we can figure out birth year and just put it in the, yes. One of the reasons that I kind of like to bring up computed columns is a lot of existing applications have them, and if you are doing something where you're going to run into some of these problems and you have the option to say, let's just not use a computed column, let us persist the data ourselves, that would get you out. You could put it in your non-clustered column store, right? It would be persisted in your clustered column store. Yes, you would avoid all the wackiness, yes, and that would be good. Yeah. All right, and so we move forward. One little note, I am showing my demos on Developer Edition of 2017. Developer Edition is awesome. It has all the features of Enterprise Edition. I did tell you at the beginning of the talk that one really cool thing, though, is we can do stuff. We can have column store on Standard Edition and partitioning on Standard Edition now. So one of the things I didn't actually expand too much, if we looked and expanded our actual time stats, I have 4 cores, you know, not a lot, but I'm proud of them. And it used all 4 cores for me for my non-clustered column store query. If I had Standard Edition and was running this against Standard Edition, there is a core limit on column store, and there are some limits as to how much memory it can use as well. I would only get max stop 2 for all, but I would still get batch mode. I would still get a lot of really cool stuff, but fewer cores is going to be slower for a lot of our queries. So this query run against Standard Edition, total elapsed time 2.8 seconds versus 1.9 seconds on Developer Edition. If you're working with Standard Edition in production and you've got Developer Edition that you're testing against, you may have slow, right? You don't have the core limit. So be careful. You might want to fake out that max stop as well, right? So just a little note. It's awesome that we have this stuff on Standard Edition. And you get all of partitioning on Standard Edition. But with column store, you don't get all the awesomeness unless you pay the big bucks, right? Problem query number 2. And this is the most famous query regression with partitioned tables. So we kind of warmed up with the problem number 1. Here's problem number 2. It's the max-min problem. There's also issues with top. You know this is going to be a hard query to optimize because of the complexity of the query, right? I mean, like, look at it. Select max first name ID, which is ridiculous, I know, but I have an integer column named first name ID. The only important thing about this query is that I'm just looking at a single integer column, and I want the max value from it. And I do have a row store index on first name ID, right? So should be really easy to find the highest first name ID. And we're going to look at it against the partition table and the non-partition table. How could this query be difficult? It's always been fast before we partitioned the table. What is up with it? This problem is also was the inspiration for the session after a SQL Saturday. I'd done a session where I was talking about some query tuning, something or other, and a fellow came up to me after the session. He said, "We ran into this problem after we partitioned our table. I think you should include this in a presentation because it really stinks to figure it out, and other people should know about this because it's not that bad. Once you know about it, you can fix it, but people should know. So people should know." Here's our query against our original table, right? Just like I had on the slide, but against the original table. And I'm going to turn my plans on. And oh, wow, that's speedy. My execution plan is nice and simple. So I'm going to highlight my select here. Let's look at our query time stats for the whole plan. I mean, we managed to use no CPU time at all. Okay, we must have used some, but it was so small that it didn't even register, right? Like, oh yeah, we had a little bit of elapsed time there, but whoa, that was easy. Well, this says index scan. I've heard that scans are bad and seeks are good. I mean, I've heard that. I don't know about you, but how could this scan be fast? Well, SQL Server is very clever, and every scan is not necessarily a full scan. With my scan highlighted, if I look at the properties, there's one very important thing. I'm looking for the max value, and it said, hey, this index is sorted on first name ID. I'm going to scan to one end of the index, find the top value, and then just stop my scan because I found it, right? So this scan is just like, boop. Every scan is not bad, and this is just one of the things. Yes? Great question. Is the backward scan new? The backward scan is not new. We've had this, I think it's even in 2005, backward scan. There are a few little limitations that come along with backward scan. The zone of the query that it's in will always be single-threaded. In my case, I'm just doing like, who cares if it's, right, it's just really cheap. It can be SQL-threaded. So yes, it is in prior versions. It does have a few limitations that come with it, and SQL Server will just do it automatically, and you'll see it in that plan here if it happens. Yeah. So Paul White, who I mentioned earlier, he has a great blog post about things that make things single-threaded, and he talks about the backward scan. Is there a hand? Okay. All right, so this is fast. Well, Okay, I mean, against our partition table, like how slow could it be, right? So I'm going to run this against our partition table, which has an index on first name ID. I am telling it just use the row store index. We're not worrying about the column store right now. We'll get to that later. But use the row store index, and okay, this used to take 0 time at all. That just took 10 seconds. What's up with that? Well, what is up with that? First off, I'm going to just confirm, yes, it really did take 10 seconds. It really did. But we'll look at our query time stats too. We went from no time at all to 10 seconds. It's a little different. It's a small difference. Looking at our query time stats, yep, 41 seconds of CPU time, right? It took a little bit. Well, what happened? Here's a clustered index scan on this table. Am I missing an index? We should have a non-clustered index scan. Let's take a look at our table, actually, on PT first name by birth date. We're going a little off-road, but it's for the good of us all. SP help index, and it's not going to show us that. It will show me my index names. It's not perfect, but sometimes we have to deal with things that aren't perfect. Come on, connect again. Hit my safety there. Do I not have my index on? I have my index on first name ID. I want my max first name ID column. Non-clustered, located on. Oh, I need the actual index name. That would help rather than putting the index key column in there, right? All right, I'm going to do estimated plan. All right, well now, I am going to look into later why that was not selected, but let's run this and see how long it takes. So now, I mean, I'm kind of doing sort of two things here, but I'm leaving them in there on purpose. I'm saying ignore the non-clustered column store index. That'll mean I'm not going to get batch mode. I don't want to cheat and get batch mode here just because a column store index is on the table. But I also am forcing it to use the non-clustered index on first name ID, which it didn't want to choose for reasons I will determine and write a blog post about later. But looking at my execution plan, all right, well, how long did this take? This demo is more interesting than I even realized before today. I love it. Looking at my query time stats, this did take more time than no time at all. It took 9.7 seconds, and it took 36 seconds of CPU time, right? So actually very close. Looking at our plan, we have an index scan of, let's make sure I'm like, I told you, I forced you to use my index, so boy, I hope you did, because yeah, you've got it. Okay, we did scan first name ID. Looking at our properties, did we get a backwards scan on first name ID? We did not get a backwards scan on first name ID. And then also, like, remember, we did a backwards scan on that, and there was just a little bitty arrow with like a little data coming out before, and now I have a lot of rows coming out of there. Our partitioned index is much slower, right? So we went from no time at all to 9 seconds. Why is that? We're going to look at some slides and then talk about speeding it up. And I'm making myself not figure out, for time reasons, I'm like, no, you can't figure out why it's not using the index now. You have to save that for later, Kendra. All right, so what happened? With the non-partitioned index, it was real easy. Went straight to the top, did the backward scan. Sweet. But as soon as we partition the index, this index is on first name ID, right? We have a key on the index of first name ID. Each partition goes for that year, low first name ID to high first name ID. And SQL Server decided to find this max value, I need to go in every single partition, and I need to scan it, right? You look at this, I mean, I look at this and I'm like, well, why didn't you just do this, right? Like, okay, to find the highest first name ID, it could be in any partition. Theoretically, you don't have a guarantee it's not, but why can't you just go to the top of each partition? Why can't you just do a very quick backward scan in each one? Well, we have a bug on connect.microsoft.com. Let's look, it had a birthday last year. So it was born on November 26, right after Thanksgiving, 2006. As I looked this morning, it's up to 121 votes. You can make a difference. You can vote for this and say, I would like you to fix this. You're doing all sorts of other cool stuff with the query processor. Please fix. Please do be polite in the comments. There's some rage comments in there of people who I think were woken up really early by this bug and then just got a little irate. Just, say, I can reproduce this. I would like you to fix this. Yeah. So vote it up. But basically, this bug says, when it comes to these max queries, when it comes to these min queries, when it comes to these top queries, the optimizer gets a little drunk. And it could be a lot more sober. And I think it should be more sober. But we can, as the commenter said before, we can make it be more sober. We can force it to do that little bitty backward scan that we wanted. And min does have the same issue. I'm just showing max today. So a couple different fixes. One fix which I'm not going to show because it takes two minutes, to, just like the last demo. If we create a non-aligned index on first name ID, that is not partitioned, we can get the same performance we had before. We have all those downsides. Can't truncate partitions, can't do partition switching, have this big growing index. That does work because it gives us the same structure we had before we partitioned the table, but it's a bummer. So what about the query rewrite? This query rewrite in that bug, Eric Hansen, who was a program manager at Microsoft, he's doing something else these days, very smart guy, he said, okay, I see your pain. Here is a T-SQL workaround that you can adapt and leverage to get around this problem. So I did not come up with this. I am just following, actually, the workaround on the bug. The first example here is just showing you how this partition keyword works. Right now, this query is just looking at a single row from my partition table. And I'm saying, I want to know for fake birth date stamp, which is my partitioning key, tell me what partition it's in. And it says, oh, well, that row is in partition number 14. For every row, SQL Server knows what partition it's in based on that partitioning key. And we can leverage this in our query if we want. Here's a simplified version. It's going to get more complicated. This is the simple version. What I'm doing here is I'm saying I want the max of max val. We'll see max val in a second, from two things. The first thing here is I'm using a table value constructor. I'm using the values keyword to say I want to have a little 3-row table. The first row has 41, the second row has 42. I've just hard-coded these numbers for this example. So I have a 3-row table with 41, 42, and 43. And then I'm going to do a cross-apply. In the cross-apply, I select the max first name ID, and I refer to that as max val. That's where max val comes from the partition table. And then I've got a where clause that says where the partition number of that row is equal to partition table dot num, right? My table value constructor. So I'm basically saying I want to gather in this cross apply, I want to get the max first name ID for every single partition, and I'm forcing that by the use of the partition keyword and joining to the table constructor. And so I get the max of each partition, and then I get the max of all the maxes in the outer query. Very simple, right? Very simple. Super simple. I say that with deep sarcasm, very deep sarcasm. Well, it is fast, right? I'm only looking at 3 partitions, right? But I ran this and looking at my execution plan, so I don't necessarily have the right data. This is a prototype. Looking at my select operator, my query time stats, well, it's not 0 milliseconds, but I'm going to say it's good enough. It's 1 millisecond. Here's my constant scan is my table value, or my row constructor. And then for every row in there, I go do a nested loop and I find the max. Let's look at the properties. Come on, we can do it. And in that little scan there, I am getting it smart enough when it's looking at, thank you, tooltip, when it's looking at the individual partitions, it is smart enough to do the little backward scan. And then I do the max of them all. Okay, well, I don't just want this for 3 partitions. And what if I have changing partitions over time? Maybe I'm adding them. Maybe at some point I archive a bunch. We can see for our partition function how many partitions it has. What I'm doing here is I'm looking at a column called fan out. in sys.partition functions, and then I'm joining it to a numbers table that I've created with one row with numbers, and I'm saying, okay, I want one row for every partition in my table right now. Instead of hard coding that row constructor with set ones, okay, give me my partition numbers that I have right now, and I can tie this into my query. I think this is my third Paul White reference of the talk. I'm only at 3, sometimes it's higher. He pointed out in one of his blog posts that if you join to a system table, that article on things that prevent parallelism, joining to a system table kills your hopes and dreams for having possibly multiple cores. So I am doing 2 queries here. That's why I've got I figure out my fan out in one step, and then I use my fan out in the next step. I'm not doing it all in one, but I can, with this very simple query, right? I can figure out my max first name ID very quickly, and it will still work even if I'm changing partitions, and I get a parallel plan down here, and I can actually get my data back quickly. So if I look at my properties here on my query time stats, okay, well, I'm going to call 13 milliseconds fast enough. It's not 0, but the 0 is a lie anyway, right? The 0 is not true. It's very simple query rewrite, right? Very simple. If you don't want to play around with this, please do vote up the bug. Please do vote up the bug. There are other ways that we might be able to fix this as well. What if I just let it use the column store index? Column store indexes are great for things like scanning and counting, and I don't have any weird computed column in here this time, right? Going with stuff that's in the column store index. If I let it use the column store index, it's not 0 seconds, but it didn't even need to go parallel. Boop, boop, boop. Looking at our properties here. Our query time stats. Okay, well, 1.7 seconds, 16 seconds. I mean, that's pretty good for what it's doing. And there is some real magic in here, actually. Notice how small this row coming out of the column store index is. So I highlighted this row here. This row is actually, this 0 rows were output. We did get data back, but it output 0 rows. It's trying to tell us something here. Looking at the properties of our column store index, there's something called actual number of locally aggregated rows. This is an enterprise feature. Now, we did get batch mode. That's not just an enterprise feature, but this part here is enterprise. It was able to push down the aggregation deep into when it's actually pulling data out of the column store index. It didn't have to drag all this stuff up into memory. It was able to do and figure out that max value as it was pulling the data out of the column store index. And this is a little bit slower on standard edition, as I'll show you, because standard edition doesn't have that. Another part of the magic is I got batch mode with a single-threaded query. That started in SQL Server 2016. Before SQL Server 2016, you'll get row mode against the column store index for single-threaded queries. So version matters, addition matters, lots of this stuff matters. But that column store index is, I mean, it's not as fast as the original, but it's going to be fast enough for a lot of purposes, right? Really just good, right? Love the column store index. Yes? Yes. So the comment is, I just changed from 2014 to 2016, but I haven't changed my compat level yet. And there are like a lot of things can change with your compat level, but you get new features and new things happening, like the availability to have batch mode against single-threaded queries for column store indexes. I attended Nico's pre-con on column store indexes the other day, a fantastic talk. He recommends, and I think this is great advice, make sure you've got query store on for a while if you're on 2016 before you raise the compat level, so you can collect, here's how things are performing. So if I do hit a regression after I change the compat level, I can then figure it out, right? So that'll help you in case something involved in the compat level doesn't help. I'm running developer edition, so I did get these actual number of locally aggregated rows run against a standard edition instance. Notice the line coming out of the column store index is now really big. That's because it isn't able to push that predicate down. It has to use the hash match to figure out a lot of stuff. It gets slower, but it's still pretty darn fast. It's still pretty good, right? So it can help make up for that. When we hit the min-max top problem, I prefer rewriting the query. Blasting through it with column store is an option. I would prefer not to do the non-aligned index. I would prefer to avoid. I like to align. I'm a conformist. All right, problem number 3, and this one is faster. This is, I like to end with something quick. The unexpectedly blocked query. We've got an update statement that's locking one partition in our table. And now that I look at this slide, it says the partition holding 2015 data. When we look at the query, that's not 2015. So don't read the text at the top of the slide. We will look at this in a query and see exactly what it is blocking. The unexpectedly blocked query. Here we go. All right. I'm going to copy this query into a new session. I'm going to turn on execution plans, and yes, we are holding a lock on 2010 is where this row is. So we are, let's say we've got an update running. Hopefully we don't have a lot of transactions just sitting around open in production, but in this case, for demo purposes, we do. I'm highlighting the clustered index update, and I can see that my clustered index update on my partition table is accessing only one partition, and it is partition number 53, right? So it is eliminating partitions and only doing its update in one. This is good. This is good. So queries accessing other partitions shouldn't have problems, right? Let's get back to our actual demo here. This query is reading from 2000, right? The other one is doing 2010. So this query, which wants to count the rows in the 2000 partition, shouldn't be blocked, right? Oh, well, it's slow. I'm going to open a new window, and I'm going to run a command using the free SP-whoisActive procedure written by Adam Mechanic. And I'm going to say, oh, what's going on? What's happening here? What's happening? Well, oh, I do have some blocking. My count query is blocked by what shows as set statistics XML off because I turned on my actual plans in that session. That is my update. It shows as funny because I turned on actual plans. So I have to know what it is if I'm using actual plans. Well, why is it being blocked? I'm going to look at the query plan for the blocked query. What is it? Shouldn't it just be reading one partition? One of the tricky things with table partitioning is telling what it wants to read from. It's using the column store index and looking at what it's doing. Okay, we've got a predicate here that's saying, like, I don't get actual partitions access. This is not an actual plan. I can't just go over to the properties and be like, what partition range do you want? This is a cached plan, which doesn't have actual stuff in it. It's just like, here's what I want to do. Well, what I want to do is, I don't have a seek predicate. I have a predicate that's like a filter. And my filter is saying, I want to look at this column, and wait a second, there's an implicit conversion here. I put a literal value in, but there's a parameter value here. What is up with that? I put a literal in there. Well, if I give SQL Server very simple queries, it will do what's called simple parameterization, also known as auto-parameterization. And now I've got lots of windows open. We're going to go back to our original window. There we go. What SQL Server is doing is it looks at my query, who we're going to stop, and it said, oh, this is a very simple query. Instead of using these literals, I'm going to auto-parameterize these so that the execution plan can be reused. If I had on the database setting forced parameterization, it would do this to even complex queries. But even for simple queries, I don't have to have the database setting on. What I did in my query is I gave it an untyped date-time value. My partitioning key is datetime2 with a precision of 0. I did not give this a precision. When it auto-parameterizes, it's like, oh, let's give it a precision of 7. That's the highest we can have. It doesn't know to match. So it guessed that it gave me an implicit conversion to a higher data type. That meant, since it was a higher data type, it had to check every single row in every single partition. When you are partitioning, the data type of your partitioning key is really important. If I change my query and I explicitly say, I'm still doing a type conversion, but I'm saying make it datetime 0. That is the type that I want. That is the type that matches my partitioning key. I don't get blocked. And when I look at my query and I look at my plan, I can see that I get, this is an actual plan, so I can see that I actually do get one partition accessed. It's partition number 43. And let's zoom in here. Notice that I do now have a seek predicate. I also do have a filter predicate at the top, but I do now have a seek predicate. If this was looking at the cache plan, I would see a seek predicate. I would see something different in there as well. So data types are incredibly important, especially for your partitioning key. If you want to get partition elimination, you have to use your partitioning key and you have to use the right type. And if you have users who are writing queries against this table, you need to help educate them of, okay, please be very explicit about your types. Yes? For date for birthday, the question is, do you use datetime2 only for demo purposes? What if I wanted to know the time of day they were born, though, and I wanted more granularity? And maybe this is a scientific database, and I even have the milliseconds that they're born, right? So I'm trying to use, I do think people use datetime2 a lot, which is why I chose it, I think, just for practical reasons, and folks do sometimes run into this one, so. My big message today is that table partitioning is awesome. It's simply not magic for existing query performance. It's not, you can't just sprinkle on table partitioning and whoa, my queries are faster than ever. It is magic for data loading, for data archive, and for specialized coding practices where you're really leveraging the partitioning. You can make things really fast. It just isn't necessarily going to do all the work for you. So we saw cases where we could no longer get a stream aggregate because we had changed the structure of our index. We got a hash match or a hash aggregate. We saw those crazy min-max top. Please vote for the connect items. Please vote it up and say, hey, I'd like for you to fix this. And we saw that data types really matter. Please just don't, when you run into issues, don't just jump onto the non-aligned index solution. Please look at, are there other ways we can fix this? Because down the road, those non-aligned indexes will limit you. They'll become really bigger and bigger and harder to maintain. If you're able to use T-SQL changes or other index changes to make it faster, it will scale better in the end. So top tips for partition queries. If you have Query Store in 2016 and higher, it can help you capture what are the plans for my workload, and when you're dealing with any kind of regression, figuring out what did my plan used to be makes your life much, much easier. Actual execution plans where we could see that actual partition count and the actual number of partitions accessed, like whenever you can run the query and get an actual plan, whenever that's safe, that also makes your life much easier because figuring it out from the cached plans is trickier. And if you have to kind of guess, well, how many partitions are you hitting? And you can look at, like sys.demexec query stats and see the logical reads. Sometimes you can kind of make a guess based on how many reads it did if you can't get the actual plan. Thank you very much. You've been a wonderful audience. Love the questions. Thank you so, so much.